Hello everyone, my name is Yu Shi. Today I'm going to present a study in collaboration with Professor Zhou Zhu from Worcester Polytechnic Institute and Professor Vincent Charles from University of Bradford. In this study, we focus on data science techniques and methodologies that have been applied in productivity evaluations. The study aims to provide an outlook on future research related to data science and productivity, as well as shed light on potential research orientations. In recent years, the emergence and prevalence of data science created more opportunities in operations research and advanced both the methodological and applied realms of operations research. Productivity plays an important role in research areas including economics, operations management, agriculture, engineering, and many more. The definition, conceptualization, and formulation of productivity underwent a significant transformation since the early 1950s. Malmquist, 1953, first touched upon this topic from a consumption perspective by introducing a distance function-based quantity index, namely the original Malmquist index, which was later employed to capture the productivity change between two different times. Caves et al. 1982 extended the research on productivity measurement by redefining the Malmquist Productivity Index, proposing a framework for productivity measurement that does not proceed from a continuous time representation. Their work also showed the mean of the two Malmquist output indexes is equal to the Tornquist output index, and the mean of the two Malmquist input indexes is equal to the Tornquist input index. Fair et al. 1989 relaxed the restriction on multilateral productivity to allow for freely disposable undesirable outputs and calculated the Malmquist productivity index using non-parametric linear programming. Following this, Griffith, Touch, and Lowell, 1995, demonstrated that in the presence of variable returns to scale, the Malmquist Productivity Index measures the productivity change incorrectly, and linear programming techniques might amplify such bias. In order to search for a more accurate and unbiased productivity measurement, Burek, 1996, derived a Malmquist total factor productivity index that is suitable for general production structures and capable of overcoming the drawback of the traditional Malmquist index, which does not measure productivity correctly under non-constant returns to scale. This study views productivity as a ratio between an output quantity index and an input quantity index. This is in accordance with the fundamental definition of productivity. More recently, productivity has been commonly adopted by scholars in various fields, such as the ratio between the level of outputs and the level of inputs. Waller and Fawcett, 2013, suggested that data science stands for the application of quantitative and qualitative methods to solve problems and predict outcomes. Provost and Fawcett, 2013, defined data science as a set of fundamental principles that support and guide the principled extraction of information and knowledge from data. Van der Aalst, 2016, defined data science as an interdisciplinary field aiming to turn data into real value. The underlying characteristic of data may be big or small, structured or unstructured, static or streaming, but the real value may be provided in different forms. So in this study, we try to answer the following research questions. First, what is the current trend of research for studies integrating data science and productivity? Second, what are some commonly used data science techniques in measuring productivity? Third, what industries and fields use data science algorithms for productivity evaluation? And fourth, what research questions have been addressed in each of the application areas of data science and productivity? For the methodology part, the platform we use to conduct the literary research is Web of Science. We included 3 different databases, including the Science Citation Index Expanded, Social Sciences Citation Index, as well as Emerging Sources Citation Index. In order to search for the articles, we use two sets of keywords in combinations. The first set consists of data science techniques including artificial intelligence, big data, data mining, data science, deep learning, machine learning, statistics, support vector machine, and regression. For the second set, we used productivity, performance, data envelopment analysis, Monquist index, total factor productivity, non-parametric efficiency, meta-frontier, and efficiency. In order to exclude some papers from the very large data set, we only included papers that evaluated productivity using data science techniques or explored the effect of data science technologies on productivity. The articles cannot be pure methodological or a survey. The articles must have been published between 2005 and 2020, and all articles were published in journals ranked 4-star, 4, 3, or 2, according to the ABS 2018 Academic Journal Guide, unless the study had a higher citation count. Some articles in our dataset were published on non-business journals, and these articles were manually reviewed. And lastly, conference proceedings and early access articles were excluded. Next, for the bibliometric analysis, we present a table for the descriptive summary of the dataset. So after the screening process, we ended up with 533 documents, and they're coming from 52 different sources. There are 1,614 different authors' keywords. The articles came from 54 different countries or regions. The time period covered in the study is from 2005 to 2020. The average citations per document is about 23. There are 1,013 different authors, and these authors appeared for 1461 times. So this figure here presents the annual scientific production. On the horizontal axis, we have the number of records. So we can see that from 2005 to 2020, the annual scientific production exhibits a fluctuating but increasing trend. So in this table, we have some of the most relevant sources. These sources were determined according to how many papers they published. So the first one on the list is European Journal of Operational Research, which published 125, followed by Omega, the International Journal of Management Science, which published 72 articles. And then we have Annals of Operations Research, which published 47, Journal of the Operational Research Society, International Journal of Production Economics, Socio-Economic Planning Sciences, Transportation Research Part E, International Journal of Production Research, Decision Support Systems, as well as Computers and Operations Research. This figure shows the source impact. The source impact was calculated using the total citation count of these journals. So right here, we have 10 most impactful journals. The first one is European Journal of Operational Research with almost 4,000 citations, followed by Omega, the International Journal of Management Science, International Journal of Production Economics, Transportation Research Part E, Annals of Operations Research, Journal of the Operational Research Society, Computers and Operational Research, Decision Support Systems, Socio-Economic Planning Sciences, and International Journal of Production Research. We also have a list of the most relevant authors. So these authors published the highest number of articles out of these 533 articles in our data set. So there are 3 authors who published 10 articles, followed by the next 5 authors who published 9, and then the next 4 authors published 8 articles, and the rest of the authors on the list published 7. This table here shows the sum of times cited per year. So from 2005, these articles were cited 0 times. However, this number kept increasing over the years, and in 2020, the sum of times cited has increased to 1236. Please note that for the year 2020, we only included up to June because the study was conducted in June. So at the end of the year, this number should be even higher than that. And this table here presents the countries and regions of the publications. We can see that the United States is the top one on the list. 114 articles came from the United States, and this constitutes about 21% of our entire data set. And that figure is followed by mainland China, which published 90 articles, followed by Taiwan, 80. And we also have England, Spain, France, Canada, Australia, Portugal, and Greece on the list. For the empirical review, we classified these articles according to the research areas. So this table here presents the industries or fields that these studies addressed. For example, business and economics, for this category, we have 316 records. For civil and mechanical engineering, there are 118 articles. For manufacturing, we have 47 articles. For transportation, we have 26. And then we also have agriculture, environmental sciences and ecology, geography, social sciences, public administration, automation control systems, as well as telecommunications. And then we classify these articles according to the data science techniques or methodologies that they used. So these are all the different categories. For the first one, we have artificial intelligence, and 15 papers actually used this technique. And then we have big data. 18 articles used big data, canonical correlation analysis, classification and regression trees, cluster analysis, conjoint analysis, correspondence analysis, data envelopment analysis, data mining, decision trees, deep learning, discriminant analysis, and factor analysis. We also have gray prediction model, machine learning, neural network, random forest, Bayesian model. And for the regression category, we have different subcategories. In particular, these address the specific regression technique that the papers used. So there's 1 paper using Cox regression, 7 paper using kernel regression, and for the lasso regression, there's 1 paper. There's also logistic regression, ordinary least square regression. We have principal component analysis, quantile regression, ridge regression, as well as truncated regression. There are also 3 papers using support vector machine. So next, we discuss in detail some prominent works in data science and productivity. So starting from Felix Run et al., 2009, they proposed and implemented an enhanced multiple criteria framework for intelligent decision support systems evaluations. The integrated framework overcomes the limitations of some previously developed models by composing a more systematic, architectural, and computational mechanism that accurately measures the decision value of IDSS. The article highlighted the amalgamation of AI and productivity evaluation by creating advanced AI-enabled algorithms for solving the practical problem of evaluating decision support performances. Alternatively, Other studies have concentrated on the interplay of data science and productivity by studying the effect of data science on productivity measurements and improvements. Moselli and Kahn, 2012, used fuzzy subtractive clustering, neural network modeling, and stepwise variable selection procedure to rank the parameters that affect construction labor productivity. Fayek et al. 2005 used fuzzy expert systems to effectively model and predict industrial productivity. Big data is another eminent concept of data science. In the literature, existing definitions of big data focuses on its large volume. Big data can be considered an information asset that is characterized by high volume, velocity, and variety whose transformation into value requires technological and analytical methods, according to De Moreau et al. 2016. Among studies on big data and productivity, some salient works include the article by Gupta and George, 2016, who investigated the influence of big data analytics capability on firm performance. They corroborated that higher BDA capability leads to superior firm performance by firstly identifying resources that contribute to a firm's BDA capability, developing the instrument to measure BDA capability, and finally testing the relationship between BDA capability and the firm's performance. Moreover, Mueller et al. 2018 analyzed the relationship between BDA and firm performance based on objective measurements of BDA assets. They found that while information technology-intensive firms gained productivity improvements from BDA, this improvement was not detected for firms in other industries. Song et al. 2018 investigated and summarized the use of big data in environmental performance evaluations. For the data mining category, Cole and Ose Bryson, 2006, explored the impact of information technology investment on productivity. Sivlikli and Kaya Ozirmidokos, 2010, examined the improvement of manufacturing productivity via data mining. Balaba et al. 2012 developed a procedure using data mining techniques to optimize the maintenance plan and improve underground mining productivity. Ramesh and Vardhan, 2015, applied data mining techniques such as density-based clustering for the crop yield prediction. For the machine learning category, Rebai et al. 2020 proposed a machine learning approach to predict the productivity of secondary schools using DEA in the first stage and machine learning techniques in the second stage to map variables associated with higher performances. Likewise, Appiah-Hain et al. 2019 also combined DEA with machine learning algorithms. They studied the impact of information technology productivity on bank efficiencies and verified that information technology has a significant impact on bank performances. Ballester et al. 2019 developed a novel machine learning approach for evaluating the productivity of university researchers. Next, we conducted an analysis on the keywords. So this is done by the bibliometrics tool by Area and Kakurullo 2017. And this figure here shows the 10 most frequently appearing words using the keyword plus. And from here, we see that data envelopment analysis and the short form DEA were on the list. This shows that most of the techniques used in our dataset are related to DEA. It can also imply that DEA is one of the most frequently applied data science approach in the 533 articles. Therefore, we select some top studies regarding DEA and productivity to discuss in detail. Banker and Natarajan, 2008, proposed a DEA-based stochastic frontier estimation framework to evaluate contextual variables affecting productivity. The framework consists of a two-stage procedure involving DEA and OLS regression. Liu and Wang, 2008, measured the Monquist productivity of semiconductor packaging and testing firms by employing DEA. Barrows and Papak, 2009, evaluated the operational performance of European airline companies using DEA and bootstrap truncated regression. Chowdhury and Zelenyuk, 2016, analyzed hospital service productivity using DEA and truncated regression estimation. Similarly, Du et al. 2018 also proposed an algorithm combining DEA and truncated regression, and the algorithm was applied to measure the productivity in the banking sector. Samoylenko and O.C. Bryson, 2013, proposed a DEA-centric DSS for performance evaluations of productivity-driven organizations. Chu et al. 2018 formulated a Slack-based DEA model for environmental efficiency evaluation involving big data. Further, the computation time of this model was reduced with the aid of a parallel computing design. In conclusion, in this study, we reviewed the applications of data science techniques in productivity. From the bibliometric analysis, we observed that the usage of data science techniques in productivity has been growing since 2005. From the empirical review, we were able to identify some most frequently studied industries, top research areas, and popular techniques. Overall, many research outputs have contributed to the improvement of productivity in various sectors and industries. Although there are various purposes of integrating data science with productivity, the interplay between these two is often manifested through three major aspects. The first one being using data science techniques to evaluate, compare, or improve productivity. Secondly, studying the impact of data science advances on productivity. And thirdly, identifying the influence determinants or drivers of better productivity using data science methodologies. The emergence of data science applications creates research potentials. Future research can be oriented to applying multiple data science techniques in studying productivity. And research can be directed towards industries such as construction, manufacturing, transportation, environmental sciences, hospitality, banking, and healthcare. Thank you for listening to this presentation.